Hello everyone, and welcome to another video about the industrial warehouse design, in which we're going to discuss the loads or actions. Now this video is part of an ongoing video series that talks about the theoretical principles of designing industrial warehouses. I will link the list of the playlist on the top right. And in this video we're going to be talking about what the factor of safety means, combinations, permanent actions or loads, variable actions, thermal actions, cranes, accidental and equivalent horizontal forces. So sit back, relax, and enjoy the show. Alright, now before I start, I want to finish some ideas in my head that I missed to talk about last time. You see, there is a slight difference between what is being used as architectural or actual dimensions and what is being inputted in the software. I just wanted to mention this very quickly, that we are actually inputting center to center. For example, the clear internal height is different than the height to the eaves. We've done this, but the idea is that the clear internal height is a little bit different because you have a cutting depth that you need to take into account. You have to take into account the fill that you will fill because you're going to put a finished floor level and so on. Similarly for the span. I mean, take a look. This is just a small thing that I wanted to say, because when you draw the drawings or let somebody draw them for you, a drafter, then he will be drawing the right side. The left side is your robot or ETAB or whatever model. The second thing I want to talk about is stabilization, because my Autodesk robot video, which will drop within the next day or two, is going to be talking about this only, about the stabilization. I will not be talking about the loads in that video. So to talk about stabilization, what are my options? Now, please notice that I'm relying heavily on the material shown by they call themselves SCI, by the Steel Construction Info, and they have really good juicy material that you should take a look on. So the first option here is, well, they are using here full frame action. You can see that the beam here is big enough to hold the purlins in place, and here you are relying on the beam action for stabilization, because there is I don't see bracings, to be honest. I don't see those cross bracings, the typical ones. Another idea is to use an eaves strut or tie, which is basically this. You can see here that there is a strut or tie moving in the entire eaves. This one that I'm coloring right now, this is a strut, and this one is the same, it's a strut. And the question is, well, how does a strut stabilize, right? Because a strut carries axial forces. So how does this bar stabilize the structure? Well, the idea is, if you have a portal frame like this, at least the theory behind it is, and I hope I can do it in robot, the theory behind it is, if you have a portal frame like this and you brace this bay, if you try push it, this bay will resist, and the resistance is transferred via this continuous strut. And according to what I see, I believe the strut carries only axial forces. This is what I believe, honestly. You can also see those cool details about the purlin. You can see those cool details about the purlin connection. I cannot see any stabilization of the bottom flange here, maybe because they have not yet provided the cladding. But I don't see a connection even here, so maybe I'm wrong, I don't know. Notice that there is a stiffener here because the compression of the haunch will impact the column here, which gives you a stiffener here. It seems for this portal frame, there was no need to make a haunch at the apex. Maybe the distance was not that much. It depends. Here is another portal frame where you have indeed, and the reason why I'm showing those pictures is just to show you how different portal frames can be constructed. So you have the apex haunch here, you have the beginning haunch here, you still have the stiffener here, which is typical because the haunch imparts compression. Yeah, you can see there is like a purlin that seems to be connected to transfer axial forces, which should act like a strut. This is what I can see. You can also see that there is a big beam in the center that somehow also connects the entire structure, more than a purlin. Like in the center, there is something more than the purlin. Here, in the center, there was nothing. It was just a purlin. But sometimes you might want to do a full beam in the center, a bigger beam. You see, when I say it depends on your choice of the designer and modeler, I'm not just running away from the answer. This is what happens. Like, look, here, where are the beams in the center? There are no beams. Here, there is a beam. Okay, with that being said, let's dive into forces and safety. So what's the general idea? The general idea is, when you say, for example, that the resistance should be larger than the applied forces. You have to understand that the resistance is not just a point in space, but a statistical distribution. And that the applied effects or actions is not just a point in space, but a statistical distribution. And your idea is, of factors of safety, is to space the mean of the resistance and the mean of the actions so far away that the interaction here is below a tolerance in a code. This is basically your risk of failure. It depends from code to code, but I just wanted to talk about the principle of safety in codes. What are the states you need to check? Serviceability limiting states. This is about the service or function. Ultimate limit states, which means that components will fail. Fatigue limit states is basically the accumulation of damage with time. And accidental limit states is something that is abnormal, or unnatural. A reminder that we are dealing with the Eurocode this time in this video series, and we are dealing especially with the UK National Annex because the steelconstruction.info is a UK-based website or Wikipedia. There are multiple ultimate limit states to be considered. I've just put a nice little picture from ResearchGate. You can see that there is an equilibrium limit state, there is an uplift limit state, hydraulic heave or erosion limit state, geological limit state, and structural limit state. For those of you who come from the ASI code, they have different names for those. They don't use those abbreviations, but well, I guess that's a good thing. Now, design is based basically that the bad stuff should be smaller than the good stuff. The destabilizing actions should be less than the stabilizing actions. The applied internal forces should be less than the resistances. So that's kind of cool. Now, this is just a small abstract because I'm not explaining the Eurocode today. If we talk about combinations, you will see this under the Eurocode section 643. And note here that the reason of the video lectures today is not to dive into the Eurocodes themselves, because, like at least for example for the combinations, softwares like Autodesk Robots or most analysis softwares are able to produce the combinations themselves without any input from the user. So because this video series works in tandem with our robot series, I will not dive into those equations. Like I'll just an example give you. This is how you can calculate the effect of pain, I want to say. And there is a bunch of factors you need to multiply here, and you can select those factors from tables and so on. Now, the code itself needs to be read, but I will not be explaining this. Maybe I should, but this is in the far away future. For now, I am already overloaded with the stuff I'm doing right now. Check out the combinations. You should read them, but no worries because the softwares can be able to do it themselves automatically. Now, with permanent loads, so I'm referring now to multiple standards. It cannot be code neutral here because we're talking about loads now. So there is a bit standard talking about the densities, snow loads, and wind loads. I will not be talking about snow loads and wind loads today. So with that being said, usually permanent loads are related to self-weights. And you should have access to the self-weight via the density. It's totally normal. But sometimes you don't have densities. You need, for example, to go to the manufacturer himself and check out the data sheet and insulation and so on to add those loads. If you don't have them, then here is a nice table for typical roofing products and their weights. This is taken from the Steel Construction Info. And there is a very, very cool PDF that you definitely should download and add to your library at home. It's Steel Construction Info document 399. This is a 200-page comprehensive guide in designing and analyzing portal frames, so it's very, very good to read. With that being said, for the permanent loads, there are other things that needs to be added, like building services, for example, overhead lighting, piping, air conditioning, cables, and if you don't have architectural drawings, you can assume it to be between 0.15 and 0.4 kilonewton per meter square. This is once again from the reference, which is this design of steel portal frames according to the Eurocode from the SCI. You should download it and check it out. This is a cool reference. If you read it, you are then should be able to design portal frames always. Those values in the lack of architectural drawing can be assumed and should be rechecked in the final stages. For variable actions or live loads, now there are two types of live loads, right? This is a portal frame. So there is live load on the slab itself, of the cladding, and there is live loads on the ground. Now, for the live loads on the ground, we don't design our structure for it because it's being held by the elastic stiffness of the ground. We assume that the slab on the ground is being carried by the soil because there is no warehouse with a basement. So this live load nobody cares about because it's being carried by the soil. When you design the slab on grade, you need the live loads, but for now we don't need them. However, on the inclined roof, you can see that the British standard, the UK National Annex, gives you the following live loads. If your A is less than 30 degrees, which is usually the case because our angle is 6 degrees, then this is your live load. If you go more, the live load gets less. If you go total steep, then the live load becomes 0 because there is no human, unless you're Spider-Man, there is no human who could basically service this. That's not enough because, speaking of humans, if you want to test a certain piece on the roof, if it's able to carry or not, you can use an equivalent force of 0.9 kilonewtons as a human weight just to double check if there is fixing or so on. Now, there is a cool thing. It tells you this live load doesn't coincide with the snow load or wind load. This makes sense because there is no person who would go up on the roof of a portal frame during a snowstorm or a thunderstorm. As for snow load and wind load, this is stuff I will not be covering because each one of them deserves a video on its own. I believe that you are well phrased in snow load and wind loads of the British standard, so I rely on you to double check that. Of course, should CEE do a video series about the Euro code? I don't know. Tell me about this in the comment sections. But please notice that I will not be able to do this in the very near future. There are so many things I have that I want to do. But this channel is not going anywhere, so, well, tell me. With that being said, what about the thermal effects? A good rule of thumb here, and you can check out the reference, is that 1.2 millimeter expansion happens if you increase temperature by 1 degree for a 100 meter length. So let's say that you increase the temperature by 5 degrees for a 50 meter length. Then you get 0.6 multiplied by 5. So you can use this knowledge to some kind of find the expansion of anything. There is a lot to be talked about here. If the reference basically argues that there might be even a temperature rise or a stress resulting, which should be 50 megapascals. So this is really huge because this is around 18% of the yield strength of the steel. So is it really dangerous? The reference itself says no, it's not dangerous if and because axial stresses will not be realized because of slip at bolted connections. I mean, if you have bolts, usually you have a hole that is a little bit larger than the bolt. So this little difference in the distance is able to create a small space in which the bolt could slip in case there is expansion or contraction. One could say, but Dr. CE, well, look, there are continuous elements like crane runways. Those must be dangerous. No, still no, because the reference still says that you can provide expansion joints to try ignore that if you have it. Well, if you don't have all this stuff, if you just go against the entire common sense of engineering, then yes, you have to include 50.4 into account. You can do this by a multitude of... Now, first of all, I don't know why you would not provide expansion joints or why you would not provide slip at bolted connections. This is like beyond me. But just in case you don't do that, how would you deal with this? Well, in this case, you could go to your job preferences and to the S275 steel and lower your yield stress by 50 megapascals. I'm talking about robot. That's one possible way. The other possible way is to ask robot to design for 1.2 factor of safety, not 1, to kind of counteract the 18% reduction, or 1.25, I guess. So think about it. Those are two options that you could use in robot to counteract thermal expansion if you just don't want to provide any way of relieving the pressure, which is kind of strange. Talking about cranes. Now, cranes, I had a video about talking about cranes in the previous video. I will link it here. And I said in that video, I think, if I remember correctly, that there is a lot more of details talking about cranes. So here we are now. Cranes do produce vertical loads due to the crane self-weight itself, the runway beam, the hoisting, dynamic action, because when you lift something, you apply more forces. And there is also even not only a vertical force, but a horizontal force because the crane itself surges. There is crabbing. Crabbing is like a crab. Crabbing is a sideways movement of the crane, and there is also potential for light swinging. The crane doesn't swim, so there is potential for light swinging of hoisted stuff. I think my teaching assistant messed up. So yeah, now of course the big question here is, okay, if you understand this, should you take the crane action into account or not? Well, the answer is yes and no, believe it or not. I say the answer is it depends, and once again, this is not a cheap way of running away from the answer. This is actually the answer itself. Why is it the answer? Because you could have a crane that moves on its runway beam on a standalone load carrying system, or you could have a crane that moves on the runway beam that is integrated in the structure. Look at this. In this crane case, your runway beam and subsequently the crane is being carried by the columns of the structure. Whereas in this system, your runway beam and subsequently the crane is carried by a column that does not carry the portal frame. Or maybe it does. Wait, does it? I don't think so. I can see a column here. I can see a standalone column going up. Now, truth to be said, I'm not really sure about this. Maybe it is. Like, maybe the column looks like this. There was a column that I showed in the previous lecture. I will link it here, where you had this compound or column where you had the truss and a place here for the crane. Maybe that's the case here. I'm not sure. I cannot really see exactly what the column looks like. But I can see trusses here, and I can see those being my main columns, and the trusses spanning back and forth. There is not even a portal frame here. So you might have a crane being carried by its own load carrying system or carried by the general load carrying system of the hangar. For the robot video, there is a cool like A-bus overhead crane PDF where you can read more about those cranes. It's a company. I am not promoting their products here. I just wanted to show you a documentation that you might think, okay. What you would do is, if the crane is being carried by the structure, you need to know what to expect of loads, right? Now, you need to contact the manufacturer and asking about the dynamic effects. Now, because we don't have that, I will have the following assumptions. The total own weight is going to be 30 kilonewtons. This is the total own weight, basically this yellow thing with this, and the runway beams. I will assume it like this. This yellow thing with this hoist is going to be 30 kilonewtons. It still moves on the runway beam, so it's a live load. And then I will assume that the hoisted load with the dynamic is 100 kilonewtons. And I will assume that the maximum reaction on one runway is 90%. Why? Because if you have runway left and runway right, you have a motor, this hoisting machine, and this cannot just stand above the runway. It must stand, because look, if this carries 100 kilonewtons, this runway beam will feel the full 100 kilonewtons if this crane moves all the way to the left. Now, this is physically impossible because, well, you need spacing, right? It cannot just go above the runway because you need to keep the spacing here. So I'm assuming 90% to be the maximum reaction a runway can feel of the hoisted load. Of course, for the self-weight of 30 kilonewton, for this self-weight, I will assume that each runway feels 15 kilonewtons regardless where the crane is. All right, and we continue now with accidental actions. Now here I want to reference the British Code and what it says about accidental loads. Here there is only one thing I want to say, that you should assess and determine if there is anything you need to take into consideration and how. This is something really special that I will not talk about. For equivalent horizontal forces, I want to give a shout out to our dear subscriber, HR Player. He asked a question about how to model imperfections in Autodesk Robot. So I'm going to show this right now. So the idea here is that you have frame imperfections, and the British standard deals with this in clause 532. It assumes the following equation: phi being this way imperfection equals an assumed imperfection multiplied by two reduction factors, alpha h and alpha m. The imperfection is 1 over 200 assumed by the code. This corresponds to, I guess, 0.005 or something. So this is the initial imperfection. and you need to find something called the reduction factor for the height and the reduction factor for the number of columns, and then say that the horizontal imperfection force equals your phi multiplied by the total axial force. And this will produce to you a horizontal force. You can ignore this imperfection if your real horizontal force from wind load, for example, is more than 15%. So you can basically ignore this way if you have real loads of wind or snow or whatever that are more than 15% of your total axial load. Now, what are those things? This alpha h is reduction factor for height, where your h is the height of the column, and it's between 0.67 and 1. This alpha m is a reduction factor or for the number of columns. If you have a single portal, then you have m equals 2. If you have a double portal, then you have m equals 3, and so on. And you can, for example, for our portal frame, the height of the portal column is 8 meters. It's single portal frame, so m equals 2. So means that the reduction of the height is so and so, and the reduction of the number of columns is so and so, which means that phi equals the assumption multiplied by 2 reduction factors, which gives you a 3/1000. This means that you can add the equivalent horizontal force on the column top, which equals 0.3% of the vertical reaction at the column. Which means now that I will not do this. I will not do this in robot. But if you want to do this in robot, then you would have to analyze the frame or the entire structure, find the reaction first, and then take the reaction, multiply by 0.3%, and add a horizontal force at the column to simulate imperfections. So yeah, that's everything I wanted to talk about. Before I finish, I want to give a huge shout out to our dear channel members whose names are going to be on the screen. Thank you very much for considering supporting the CE channel. This helps us produce more videos and more quality videos for you. With that being said, I hope that you enjoyed the video and that it was beneficial for you. If you have enjoyed the video, then please like, share, comment, and subscribe, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.